So welcome to the workshop on magical mathematics. First of all, thank you for coming. I know there's a lot of parallel sessions going on right now. I'm myself a bit sad about missing a couple of the other workshops that are going on. So I appreciate your making this choice, and I hope it'll be worth it. Let's see. So as a warm-up, I want to start with what's called the 4-card trick. Okay, so all of you either have 4 cards or you're sitting with somebody who has 4 cards. Okay, so um, maybe I should also grab 4 cards. I don't know. Do you have 4 cards extra? Okay, I'll try to do this along with you guys. Thank you. Okay, so what's going to happen is the following. This is not a trick where I have some big reveal at the end. I'm going to go through a certain mechanic. And this is something that you can go back and, like, if you know kids that you want to play with, you can try it out with them, okay? So what will basically happen is that you make a note of whatever card is at the bottom. You can shuffle it if you want. Like if you have a favorite card among the 4 that you use. So I like the Queen of Hearts. It's easy to remember. So I'm going to put the Queen of Hearts at the bottom. You can put whatever card you want at the bottom. Okay? And what's going to happen is we are going to make it look like we are shuffling this a lot. Okay? It's going to feel quite random. So when you're doing this with somebody, really try to make it like, they're making a lot of random choices. And after all the shuffles are done, we'll do 1 or 2 moves. And what's going to happen is that this card is going to somehow pop out. Okay? So that's the intended effect. Okay? All right, so let's try this out. You'll have to sort of follow along. So everyone's made a note of the card at the bottom? Yes? Okay, super. All right, so what we're going to do is we're going to take the top card and put it at the bottom. Okay, want everyone to follow along. Take the top card and put it at the bottom. Have you done that? Yeah? Okay. So right now my Queen of Hearts is engulfed by whatever was at the top. Cool. Now we want to turn the top card around, make it face up. Okay? Everybody started with their cards face down. Yes? Started with your cards face down. So now you're basically taking the top card and turning it face up. Okay? We're doing this for the first time, so I'm going to go a bit slow. When you actually do it, these movements will become fluid. Okay. All right. Okay, give the packet a cut. What does that mean? You can take any number of cards you want. It could be 0. You could ignore this move completely. Or you could take 1, 2, or 3 cards. Okay? And so I'm picking 2. You can pick any number you want. And I'm going to move it to the bottom. Okay? Pick any number of cards you want, move it to the bottom. Yeah, so don't change the orientation. Whatever was on top goes to the bottom. Right, so in general, giving a deck a cut means pick some number of cards. Pick some number of cards from the top of the deck, any number you want, and take that and put it at the bottom. That's what it means to give it a cut. Okay. Like normally when you're shuffling also, some people do this, right? They take a bunch of cards and put it at the bottom. That's what it means. You have only 4 cards, so if you take all 4 cards and put it at the bottom, nothing has changed, okay? So usually you will want to take 1, 2, or 3 if you want to actually make a cut. Okay. All right, now take the top 2 cards out, okay? Take the top 2 cards out, make sure to pick them together, okay? And then take them together and turn it over. Yeah, has everybody done this? You gave it a cut, took the top 2 cards and turned it over, okay? We're going to do this a few more times, okay? Cut anywhere you want, take 2 cards, turn it over. Do this again. Is everybody done? Okay, give it one last cut. Again, anywhere you want. Okay, are you convinced that the deck must be now pretty random? right? Because you did a lot of random cuts and then you turned the top 2 cards over, right? So there wasn't really a lot of control in terms of, so if you're doing this with with a kid, like they can really like mess up the ordering quite a bit. Do you still remember the card that you saw at the bottom? Yeah? Okay. So the card that you saw at the bottom is in some orientation somewhere. Okay, so what we're going to do is we'll try to surface it using some magic and math. Okay? So if you have a favorite magic phrase, maybe you should say it now. If you have a favorite prayer, maybe you should pray now and hope that the rest of it works. Okay? All right. So, okay. We're going to do like 3 steps now. Okay? So turn the top card over and put it at the bottom of the packet. Turn it over, put it at the bottom of the packet. Yeah? Everyone done? Okay. Put the current top card at the bottom of the packet. No need to turn it over, just put it at the bottom. And now turn the top card and place it right back on top. Okay? Now you should fan your cards out. And what do you see? So for me, what's happening is 3 cards are facing up. Okay, so you see 3 cards, and 1 card is facing down. And the card that's facing down is the card that we started with. For most of you, it's going to be like that, or it's going to be the other way. Okay, like the card that you noted in the beginning is going to be facing up, and everything else is facing down. Okay, so 1 card is facing the other way, and the card that's facing the other way is the card you started with. Did that happen for everyone? Yeah? Yeah? Isn't that pretty cool? You want to try it again? If it happened for everyone, it's probably not fluke. So, let's see. Okay. Okay, I'm going to try and do it again. So we start with some card at the bottom, right? I have very bad memory, so I'm going to stick to the Queen of Hearts again. Pick whatever. So we'll do it again, especially for the benefit of those who joined after we got started. For those of you who have just joined, find somebody who has 4 cards, like maybe there's plenty of room, maybe share a table with somebody who has 4 cards. And let's just take a minute to reorganize. Okay, those of you who like taking notes, you don't have to because you have the link to these slides, so you can look it up later. But I know some people are compulsive note takers, so I won't judge you if you just want to put down these steps on your phone or on pen and paper. Again, you don't have to, but just to be able to replicate it. Okay, all of you settle down here? Yeah, everybody good? And we just wait for a minute. Okay, if some of you want to do it on your own, you could give it a shot, but okay. Everybody settled? Yes? Everybody either has 4 cards themselves or is sitting with somebody who has 4 cards. Yes? You have 4 cards? Okay, all right. You good? Fine. All right, so I have the Queen of Hearts. You make note of your own card, okay? All right, so what we're going to do is start off by putting the top card at the bottom of the packet. This one's an easy step. Take the top card and put it at the bottom. Yeah. Those of you who have already done this once, maybe this time you want to think about what's going on, like if there's a pattern or whatever. So when we started, we took the top card, we put it at the bottom. We took the current top card and turned it face up and placed it back on the top. Okay. So nothing much happened so far. 1 card went down, 1 card got flipped. And now what we're going to do is we're going to repeat this 3 times. You could repeat it more times if you want, but basically what we're going to do is give the deck a cut. So pick any number of cards you want from the top, 1, 2, or 3. If you pick 4, that's the same as doing nothing. You can also do nothing if you want, that's fine. But pick 1, 2, 3, or do nothing. I'm going to pick 2 and put it at the bottom. That's a cut. Okay, so in general, if you have a deck of cards, pull out some and put it at the bottom, that's called a cut. Okay, so we've given this packet a cut. And then what we're going to do is take the top 2 cards and turn them over. Make sure to pick them together and turn it over. Okay? And we're going to repeat this a couple of more times. So cut the cards at random, take the top two, turn it over. Cut the cards at random, take the top two, turn it over. And now give it a final cut. Again, anywhere you want. Maybe I'm not going to touch my deck. I'm not going to give it a cut. But you can give it a cut wherever you want. Okay? All right, so at this point, the deck should feel random. Okay? If it doesn't feel random enough for you, you could do this cut and turn over more times if you want. But hopefully right now it feels random enough. And the card that we made note of initially could be sitting anywhere in any orientation. But we are going to pull it out by doing a few steps. Okay. All right. Please say your prayers. I think they worked last time. So say your prayers or say your magic lucky phrase. Okay, and then repeat these steps carefully. So turn the top card over and put it at the bottom. Do you remember what the next step was? Take the top card and put it at the bottom. Don't change the orientation. Okay, so that's the next step. And what's the last step? Just turn the top card over. Okay, right? And at this point we are done. Let's spread our cards, and this time, this is nice for me, I have the Queen of Hearts pop out, everything else is face down. Okay, did it not work for anyone? Oh, okay. All right, this is math, so it must have been that maybe one of your steps was, okay, maybe let's just quickly give it a shot again. This time let me show you all the steps at once and everyone can do it at their own pace. Anybody else who had a problem, or did it work out for all of you? Okay, so did it not work out for you? Okay, all right, so by the way, all we are claiming is that 3 cards face the same way, 1 card faces the other way, and the card that faces the other way should be the card you started with. Okay, so there are there are multiple steps, so it's possible that you just have to be a little careful about making sure that the steps are executed as they should be. Yeah, because sometimes they're flipped, sometimes you shouldn't flip them, and so on. Okay, all right, so let's give it a shot again. Make a note of the bottom card, take the top card, put it on the bottom, flip over the top card, and do this cut and 2. Cut, 2, cut, 2, cut, 2, final cut. Okay, so hopefully you've done the cut, flip, cut, flip, cut, flip, cut. Okay, that's 4 steps. And now, you have to do these 3 steps. These also you have to do a little bit carefully. Turn this over, put it at the bottom, put this at the bottom directly, and just flip the other one. And once again, you can probably see the queen. Okay, I want you to take a couple of minutes here to think about what's going on. Maybe just think about the special case when all your cuts are like there's no cut, okay? You don't really cut. So what was the first step? We said take the top card, put it at the bottom, flip the top card over, okay? And then we said give it a cut and flip 2. So I'm going to flip 2, flip 2, flip 2, back to where I started. I'm not really cutting, I'm not interested in cutting. So I did that, give it a random cut, I don't want to cut. And then what did we do? We said take the top card, flip it, put it at the bottom, take the top card and just put it at the bottom without flipping, and just flip over the top card. So I get the queen there right on top. So in this special case, which is a simpler case where all my cuts are like I cut 4 cards every time, meaning I don't cut at all, okay? Can we analyze what's happening just in that special case? And then it turns out that there's some nice properties, there's some nice properties of this particular cutting and flipping operation that makes this particular trick work. And yes, hello indeed. What we want is, okay, I'm going to hide responses for some time. Is this okay? Shall we take 5 minutes or think about what's happening? Okay, and try and come up with some explanation. It could be for the general trick. It could be for the special case when we are not making any cuts at all. The special case is kind of, at least the execution is simple. Okay, this bottom card, the top card goes to the bottom. We flip this over. So the bottom card right now is sandwiched by the top card, the original top card, and whatever was the second card is flipped over. And now what we are going to do is take 2, flip, flip, and flip again, right? And then what did we say we'll do? We said top card flips, goes down. This goes down as it is. And then top card flips again. And that's my bottom card. Okay? So at least in this sequence, see if it makes sense, like that this is always predictable. And then how are the cuts affecting? Like the cuts feel like they're bringing in an element of randomness because every time you could cut 1, 2, 3 or not cut at all. So that's 4 possibilities in each of those 3 steps. So that's 4 times 4 times 4. That's a lot of different ways that this could go. But in spite of that, every time you end up with one of 2 things happening, which is that 3 cards facing away from you and your card turning towards you or the other way around, right? So in all of these, like no matter how random the shuffles are, things seem to come back. Okay, so I'm curious to know what you think. So let's take a few minutes and so you can ignore the timer. This is just for me to keep track of time. It'll probably take 2 or 3 minutes. There are more general versions of the trick, yes. In particular, there's this property of, there's something about the sequence that is preserved when you do this, even in a bigger deck, when you take the top 2 and flip, right, and cut. So both of these are well-known operations in card magic. So either you cut and flip the top 2, or you flip the top 2 and then you cut. So this is a special operation, and it preserves some property of the deck. And you can use that invariant to design many effects. So this effect with the 4 cards is kind of based on this property, but you can also do it with bigger decks. Yeah, this is something called, it's called the Hummer Shuffle. It's named after a chap called Hummer. And then there's a whole like family of tricks that are based on. So a lot of card tricks are like this. You find a special property of some operation, and then you say, aha, based on this, I can do something. So it's also just fun to practice these movements. So even if you don't feel like thinking about the math, it's kind of just meditative to do this a few times. And you sort of get into the flow of it. It feels like a lot of steps, but you actually end up remembering it, and you can actually perform pretty soon. Yeah, so there was an explanation for what's going on in the no-cut situation. Let's see if there are more responses here. Okay, binary search, we're somehow using stack properties, there's some randomness. Right, so I think this was the explanation we just discussed. Without the cut, the bottom card is, okay, so let's dig into this one. Let's just see what happens when there are no cuts going on. Again, let's do it together. The rest of it, I will leave it as like, I don't want to spoil it completely. I'll maybe just share a couple of hints. and leave it as food for thought, and because I have other things to show you as well. But let's just try to quickly understand what's happening when we're doing no cuts. So we have the, like somebody is saying it's useful to think of it as a stack. So those of you who have done your PDSA or whatever, it's really useful. Like one application of stacks in my mind is stacks of cards. You can simulate a lot of things using stacks, and in fact there's a nice programming exercise coming up for you if you want to take it up. But here we have like my bottom card, the one I cared about, and then I have some cards 1, 2, and 3. And so what did we do in the first step? We said we're sending the top card to the bottom, and we are changing the orientation of the second card. So what happens after this is we still have, okay, so the bottom card has now bubbled up to the second position from the bottom. What was on the top has gone down, so that's 3, and this is 2 has come to the top, but I'll put a bar to remember that its orientation has changed. So 2 is now face up, right? And 3 has gone down and 1 has bubbled up. So everything's basically shifted. Okay, it's sort of a cyclic permutation. Okay, except one of them has changed orientation. Now we don't do any cut. So every time I say do a random cut, the random cut is no cut at all. Then take 2, flip, flip, flip. So if you do this flipping thrice, what happens? Well, the bottom 2 remain the same because only the top 2 are affected, right? So the bottom 2 is still like 3 and the card I care about, Queen of Hearts. What happened here is that 1 and 2 are swapped, and 1 is now in the opposite orientation, right? And 2 has gone down here, okay? All right, so that's the current state of cards, and now something's going to happen which makes Q flip and everything else kind of become face down, okay? So what was the first step? We said flip and send the top card down, okay? So that's already 1 comes down and it flips to a normal, right? We have flipped it so it no longer has the bar, okay? So this is our new deck. Then what did we do? We said send the second card down without flipping. So now 2 comes down without flipping. So that's fine. And then we said take the third card, take the top card and flip it around. So that's Q3 bar, right? So your, whatever it was at the bottom now is on the top, and it's flipped and everything else has changed orientation. So that's what's happening. Like you can simply trace the steps when no cuts are happening. But now when cuts are happening, there are lots of different ways that this could go. So you could write a Python script to analyze all possible cases. For a Python script, it's not that many cases. It'll take care of it for you, and it'll validate for you whatever you're seeing, right? But you want to think of like philosophically, you want to think of maybe some kind of a combinatorial argument, like a transparent kind of a proof, which gives you a feel for what's going on, right? So, like I said, if we have time later, we'll come back to this. So you'll also get some more time to talk about it. But here's essentially like the property that drives this. Let's see. Okay, so this is one of the things that you can prove. It's still kind of an indirect ingredient of the whole trick. But like I think you were asking about what happens with more than 4 cards. That's also a very natural thing to ask. I think, does it only work for 4 cards? Can you do it with more? And so on. But this is a general statement about 2N cards. So suppose you have 2N cards that all start face down, and then you can basically do this turn 2, cut at random, turn 2, cut at random, or you could also cut at random and then turn 2, as we have been doing. Now, if you count so now you do this a few times, and then you lay out the deck, okay? and you look at the even positions and the odd positions, okay, it turns out that the number of face-up cards at even positions is equal to the number of face-up cards at odd positions. Somehow this is maintained, okay. This is, let's say, I mean, at the very beginning, for instance, if you just have like a bunch of face-down cards and you just do one flip, right? There are only two face-up cards. One of them is at an odd position, one of them is at an even position, right? And no matter where you cut, right? No matter where you cut, if this guy is going to an even position, the next guy is going to an odd position. If this guy is going to an odd position, the next guy is going to an even position. So this is definitely true at the first step, okay? And think about how you might do something like induction or whatever to prove this in general. This is a very nice property that, again, along with some other observations, you can try to argue what's happening in general. You can also write a little Python script if you want, which basically simulates. So think of it as, so you really, in this trick, you don't care so much about the card values, or at least in the statement, you don't care about card values. You only care about whether they face up or face down. That's all you care about. So you can initialize an array which is all zeros. So let's say 0 is face down, right? And in every step, like you can run a big for loop if you want. And at every step of that for loop, what it does is it flips the orientation of the top two, right? And then it simulates an arbitrary cut. So whoever mentioned stats, right? If you have a double-ended stack, like it's called a deck or a DQ, right? A double-ended queue, right? So then you can simulate cuts very nicely. You can take a bunch of things out from the front and then push it all from the back, okay? You have to be careful about, like, when you're doing a cut, they all have to go in the same order, okay? So that's, yeah, that is actually the same as, you can do it. Can you do it like that? Is that the same as, let's see. Yeah, I'm just wondering if you do a queue operation, like can you just say, if I want to cut at 5, so you can take the 5 top elements and then push them all back. There's like one way of doing it that's kind of correct and another way of doing it that flips the order. So you just have to be careful that you're doing it right, okay? So I think what you can do is pop and push one by one. That should work, I think. If you take the whole thing and try to snip it and like there's some way of being smart which doesn't quite work. So you have to be a little careful when you're implementing it. But anyway, you can implement these cuts with these kind of queue operations. And if you're using Python, this is basically standard list, extract, and append, and so on, right? So you can do pop, push. All of these are built-in operations. So what you do is you simulate this turn to and cut, and you keep track of, in the odd positions, how many ones are there, and in the even positions, how many ones are there. Okay, and you just assert that these two numbers are the same. Okay, and just see that no matter how many times and how random your cuts are, this assertion is always going to be true. Okay, so you can get some empirical evidence for this, but then you want to sit down and actually prove it. Okay, does that make sense? Yeah? For those of you who like writing like little scripts, this is definitely a candidate for like validating by script. Okay, so you can try to do like 1,000 cut and flips, and at every step you can get Python to check that this claim is actually true. Okay, and you want to think about how this property helps you, with like this thing here, but with random cuts. Okay, all right, so I'm going to leave that as food for thought and show you the 27 card trick, which is fairly popular. So have you people seen the 27 card trick? Okay, good. Because I didn't want to bore you, so if you've already seen it, then I would have skipped, but okay. All right. So here the premise is that we have 27 cards, which are laid out in 3 rows, 9 columns, like here. Okay, I'll get you to pick a card and you tell me in which row the card is. I will shuffle and rearrange the cards. Ask you again, shuffle and rearrange, I'll ask you again, and then I'll identify the card. Okay? So 3 questions, right? 3 questions to identify the cards. So I'm very bad at shuffling in real time. My big plan was to do it on the table, but I've tried this with kids before and it never works. So wrote a program instead, which is much more reliable. Okay. Okay, let's maybe refresh. All right, do we have a volunteer? Okay. Think of a card and make sure you answer correctly and honestly. Okay, don't trip it up. Okay. So do you want to write it down or something? Okay, think of a card and tell me in which row it is. Second row. Okay. What about now? First row, moved around. Okay. What about now? Third row. Wow. Okay. 2, 1, 3. Sure now? Is that your card? Oh, yay. Okay. We haven't met before and we do not like this, no collusion. Does somebody else want to try it? Okay, all right. Okay, let me just refresh it. Hang on. Okay. Tell me where you see your card. Second row. Okay. What about now? The first row. And now? The first row again. Okay. Is that your card? Okay, great. Okay, I think it's a very cute trick. Who knows what's going on? Okay, let's take a couple of minutes and think about what's going on and think about why are there 3 questions? What is it about 3 rows, 27 cards? So for the previous one, somebody said binary something. So that's actually a clue here, although it's 3. Don't know about binary sort, but there's binary something else that you learn when you're trying to find something, right? So think about that. And again, let's take a couple of minutes here. In some sense, yes, I think you're thinking along the correct lines. Right. So what you want to think about is how are the shuffles being done to empower your discovery of the card. And actually the way these shuffles were set up in the program, mainly because I was too lazy to do it properly, is that if you saw how we went from the second, like when you answer the second question and I did the final shuffle, you would have noticed that the grid did not change very much. Okay, ideally, and this is why like people who are experienced and who do it like on a table, you really can't make out. They will make it look like a totally random shuffle. Of course, it's not random. They're trying to keep track of something. But because they practice, unlike me, they can make it look random while they're preserving, yikes, sorry, unintended effect. But yeah, they can make it look very random while they're preserving something in their mind. We'll actually watch a number file video where there's, watch a couple of videos where they're doing variations of this trick. And in one of them, they only use 21 cards instead of 27. And there the shuffles are a little easier to keep track of. Because the shuffle is built into the mechanics. You don't have to do a lot of drama. It kind of happens automatically. So we'll see a performable version of this trick. But I'm still like to like I know a lot of people who can like it's very doable. It's just that I don't have good magician luck, so I end up screwing up even mathematical tricks, which is something. But anyway, give it a thought. Let's see if some of you can share your ideas. Let's give ourselves a minute. So the mechanics of the trick was clear, right? We asked 3 questions. Every time you told me which row the card was in, and these 3 answers were enough to always correctly identify the card. We're assuming that the person who is tracking the rows is doing it properly and they're being they're being honest with you. They're not trying to trip you up. So, okay, yeah. The last answer is kind of the closest. I mean, that's what I was after. I think binary search is kind of the spirit of it. It's not exactly binary because binary divides your search space into half every time. So what's being said here is choosing a row will eliminate 18 in the first iteration. In the next iteration, 9 is equally separated into 3 rows, causing the cards of the selected row to be sort of narrowed down, and this repeats. So that's exactly what's happening. Let's just demonstrate it in case whoever had that explanation, that was great. Okay, so let's see if this makes sense. So now we can, cat's out of the bag, so we can do this together. So let's say we pick Queen of Hearts again. So that's the first row. Okay. So now what's happening is that I know that whatever is in the second and third row is junk. I don't care about it anymore. So once you give me the first answer, I've gone from 27 to 9. Okay, so I've eliminated, in binary search, you eliminate only half of your search space. This you can think of as ternary search, which eliminates 2/3 of your search space. Okay? Now, of course, you could ask, why don't computers do ternary search? Because it seems like it should be faster because it's eliminating more things, and that's true. But notice that the question you're asking is more powerful here. The question you're asking here has three possible answers. Usually for binary search, it's a yes/no answer, right? So for binary search, you ask, is your number, so you're playing a guessing game, you'll ask something like, I will only give you yes/no answers. So I have a number, that's the standard thing, right? I have a number between 1 and 128 or something, and you say, is the number bigger than 64, smaller than 64? So you eliminate half the search space at a time. And you could try and do more by saying, is your number between whatever, let's say it's between 1 and 100, you could say, is it like less than 33, between 33 and 66, or more than 66, right? Then you eliminate more, but I may not be willing to give you this answer, right? I say I will only give you yes/no answers. So depending on what is the power of the probe that you can make, you can do more efficient search. So this is ternary search. Once you narrow it down to 9, exactly like the answer said on Menti, you have these 9 and you're only interested in these 9. So take these 9 and shuffle it, distribute it in units of 3 across the 3 rows. And again, if you have enough practice, you can do this mentally, but make it look like you're giving it a nice random shuffle. Okay? And now, of course, you know what's going to happen. So Queen of Hearts is still on the first row. So now I've eliminated 6 out of 9, and that first row gets distributed across these 3 rows. Yeah? And now, of course, when you tell me which row it is, it's like you're literally pointing to the card. Okay? Yeah, it may not be visible to you, but you're literally pointing to the card because of the information that I have kept track of. So that's how that works. Okay, so that's the basic version of the 27 card trick, and I think we already saw how it works. So, and it's great that you figured it out. So let's do. Okay, so do you guys want to see like a performable version of this where you can actually do it with very little practice? Okay, you don't have to do like totally random shuffles, and you don't have to do this thing of doing it on a computer. So let's see if this plays. Okay, so it's clearly the same principle, right? So you can see that she's distributing it into 3 columns with 7 cards each, because 21 cards now, right? And did you notice how she picked the cards up? Yeah, so whatever was like the column that he pointed to, that set of cards got sandwiched between the other 2 columns, right? And now imagine what happens when she distributes it like that. So you have to be careful about not distributing it 1, 2, 3, 4, 5, 6, 7. You should distribute it 1, 2, 3, 4, 5, 6. Okay? So mentally try to keep track of, I don't know if you took note of which card he picked, but mentally you can try to keep track of where his card is going. Okay, so this part is interesting. Now she knows where the card is. I mean, now she knows what the card is. Okay, because these 3 questions have been answered. Okay, and she could just say it and say that this is your card, but there's this extra step where the reveal is kind of made to be a little more dramatic. So, okay, so we know how she found the card. It's the same mechanics. Just remember that as you're distributing, you should do things. The pile which has the card should be sandwiched between the other two piles. And then when you're laying them out again, remember to do it row-wise and not column-wise, okay? Because when you do it row-wise is when that distribution happens, right? Does that make sense? Yeah. So everyone knows how she knew which card it was, yes? This last part is a little bit of a mystery. She knew which card it was, but now she distributed them into these 7 groups with 3 cards each. And mentally, she knows which group has the card, and the grouping is also such that the chosen card was the middle one. Like she basically knows where the card is. So one common trick, this is kind of a general thing, they make it sound like you're making a choice, right? She said pick 4 piles. Didn't say pick 4 piles to keep or discard. She decides whether to keep or discard them, right? So your audience feels like they're choosing something and they're not choosing anything really, okay? So, and even in the last step, she laid out those 3 cards, right? Said pick one. He picked the one that was the correct card, the middle one, so she discarded the rest. Had he picked the left one, she would have discarded that one and she would say pick one from the other two. So that's kind of a bit of a, like, it's a bit of an illusion. It makes it sound like you're making choices where you're not really making any choices. You just have to like think a little more about, like, basically now it's just a matter of keeping track of where the card is and discarding or keeping based on where the card is, okay? All right, so this one's really nice. There's another one which is a level up on the 27 card trick. So let's see it. Okay, to suffer through this. This is Matt Parker. I don't know if you follow Matt Parker, but I think he has a channel called Stand Up Math, which is very cool. But this is a number file. I think he's doing a guest video. This is more closely related to the 27 card trick that we saw. And this has a power up that, again, I'm going to leave as homework, but it's really nice to watch what he does. So let's try to follow along and see if we can guess what's happening. I think that's a really cool variation where you can get the card to show up wherever you want. Their favorite number has to be between 1 and 27, I guess. So get them to pick a number between 1 and 27. Whatever they pick, you can make it happen, which is really cool. Okay, let's see. I want to go back to unmuting on Zoom and hopefully not get an echo or anything. Okay, good. Right. Okay, so if you go back to the notes, you will find these links. I'm not playing the rest of the video because he actually explains very nicely how it's done. But it's, again, a really cool exercise in ternary representations of numbers. So when you say 10, you probably know how 10 is written in binary. It's 8 plus 2. But think of how is 10 written as a sum of powers of 3. It's 9 plus 1. So in some sense, in this case, I think it was a lucky hit because you had a pile of 9 cards and you could just get the chosen card to come above it and it would automatically be the 10th card. But what if the favorite number was 15 or something? That would be, what would that be in terms of powers of 3? It's 9 plus 6, so that's 9 plus 3 times 2, right? So think about, like, so this is like whatever many puzzles. So pick some arbitrary number and think about how will you get the card. And the only operations you have is basically taking these piles and putting them one over the other in some appropriate way. So you do want to achieve 2 things. One thing you want to achieve is that the card should be identified. That's the main thing. you should be able to figure out which card it is. So this distribution must happen, right? So once a pile has been identified, when you distribute it again, those 9 cards must get split as 3, 3, 3, and in the next step, whatever 3 cards are, they should get split as 1, 1, 1. But simultaneously, you want to make sure that wherever that found card is, when you collect the piles for the last time, that found card ends up at the correct, at the correct level inside the deck. You can make it come up at the top, you can make it come up at the bottom, or anywhere in between if you do the previous steps correctly. And it seems like a real challenge, but you do have some control in terms of how you're collecting the piles. So think about how you can leverage that to get the card to show up wherever you want it to. Okay. All right. So that's hopefully a nice homework problem. You can go back and think about it, and you can validate your answer by watching the rest of the video. Okay. All right. Okay. Maybe we should do 45 minutes left. So, okay, let's try. Okay, let me try this first. I'm going to need my phone. Okay, that is strange. Okay, consider this setup. Consider this trick where, okay, I have a function f. It's a black box function. It's a black box function that I have designed, but it's a deterministic function, okay? Meaning it doesn't, on the same input, it always gives the same output. There's no randomness, okay? So f is a deterministic function. It takes a 16-bit string as input, and it produces some number between 0 and 15 as output, okay? That's what the function does. Okay, I get you to select a string as input, and just like in the other trick, I'll ask you what's your favorite number between 0 and 15, okay, and I will say, okay, you chose the input, you chose the output, I'll take my function, I'll pass you input, and I'll get your output, okay. Okay, if I could pull off this trick, it would be really impressive. Can you tell me why this trick is impossible for anybody to pull off? Like, this seems like it's a bit too much, right? Can you say why it's too much? Exactly, it's a fixed function, right? It's deterministic, right? So I do one round, maybe you say, let the input be all zeros, and my favorite number is 7. So f has to give output 7 on the all zeros input, okay? But then I say, okay, let's do it again, and then you again choose all zeros, but now somebody else says my favorite number is 10. Now this function, if I was lucky the first time it worked, it said f of all zeros is 7. Now it has to say f of all zeros is 10, but it can't, right? Because it's already committed to a fixed value, right? Does that make sense? You can absolutely destroy this trick if somebody claims that they can do this. Okay, it's not possible. It's not possible because the function is fixed, right? Okay. But here's a variation. You give me your desired input and your desired output. I may not be able to get your input to go to the output, but I'll be able to get almost your input to go to the output. Like just by flipping one bit in your input, I'll be able to get the output that you want. Okay? All right. Let's see if we can make this work. So let's demonstrate once. Okay, this is my function. Right now it's taking all zeros as input, and it's the output is also 0. I can click these bits to flip them. So I'm going to crowdsource an input string, okay? So how do we do this? Maybe let's start from you and just go around. Each of you just say 0 or 1 on your turn, and I will take that as input. So we'll do this for the first 16 people. We'll repeat this a few times, so yeah. Okay, so why don't you start? 1. Okay, I'm only going to hear, so just shout out 0 or 1. You have to give me 0 or 1, yeah. Okay, 0, all right. Okay. Uh-huh. Okay. 0. Was that 0? Okay, 0. 1. Who's next? 1. 0. 1. 1. 0. Okay, all right. Somebody give me a number between 0 and 15. Okay, 7? Did you? Okay, 7, 9. Okay, we'll have to do this one at a time. Okay, let me take 9 for now. We'll come back to 7. Okay. Okay, if I press F, I get the output of the function on the given input. Okay, so what is this? This is coming out to be 3. Okay. And what did you say you wanted? You said you wanted 7. Okay. All right, I'm going to try and flip the 4th bit and see what happens. Got 7. Okay, the next one was, you said 9, right? So currently, let's say this was your string. Currently, the output is 7. I want to change it. I want to change it to 9. Let's see. I'm going to flip the 14th bit. I got a 9. Anybody else have a number they want to target? 12. Okay. It's a bit of a challenge. Okay, you don't know what I'm doing. It's totally random. I'm going to flip 5. Okay, anyone else? Okay, 0. It's interesting. For 0, I think I'll just end up flipping 12 again. Okay, maybe not again, but if you want 0 to go from any output to 0, I will just flip whatever that output is. So, 0. You want 15? Okay. Then again, I think I should just end up flipping 15. But I have I'm just double checking with my notes here. You'll know what I'm doing in a minute, so it's okay. Where do you want to, so for 15 and 0 are kind of two special cases in some sense. They're kind of the extreme outputs. So those are easy calculations comparatively. But okay, anyone else have a number that you want to try? 5? Okay, so currently it's 15. And you want to go to 5. So for this, let me flip the 10th bit. We get 5. Okay. I know this whole thing is digital, so again, there's no this is really like a genuine math trick. I'm not doing anything. I'm not doing any funny business because anyway, I have to explain it to you, right? So I don't there's no funny. So this is, let's see, I forget what the, okay, let me just to really convince you. If you want to try it out, you can go to this URL. XOR trick, and you can even check the source. So that's basically the function. It's like 4 lines of JavaScript. It does some combination of the values. Okay, so it's a fixed deterministic function. I'm just showing you the source, not to ask you to understand it, but just to convince you that there's no, like it is magical, but not in a cringe way. There's like it's nice magic. Okay, so this is really a proper function. The question is what is going on. Now I think it's just easier for me to preview it. Okay, so are you guys convinced that at least the trick works? That whenever you ask me for a different output, that I can always get to that output by flipping 1 bit? I did it a few times, right? Do you want to try it some more? Or do you want to try and think about what's going on? Should really think about what's going on a little bit. Right? Okay. Does anybody want more validation? Do you want to try it a few more times, or do you think trying it a few more times will help you think about what's happening? Okay. All right. So maybe let's crowdsource another random string starting from you. So just say 0 or 1. 1, 0. Okay. 0, 1, 1. Okay, 0, 0, 1, 1. Who's next? Okay, 1, 1, 0, okay. 0, 1, 0. Okay, so F gives me 3 on this totally random input. Now, what do you want to turn it into? 10? Okay, let's try to change 3 to 10. I'm going to do that by flipping the 9th bit. Became 10. We flip it to something else. Okay, 2. For 2, I'm going to flip the 8th bit. Okay, did we just lose the projector? Oh, it's back. Okay, I flipped the 8th bit. Don't know if you remember. We got 2. 3. Okay, we want to go from 2 to 3. I'm going to flip the first bit to make that happen. Want to go to 9? Did somebody say 9? Okay. So we are at 3. We want to go to 9. I'm going to flip the 10th bit to make this happen. Because if you keep doing this, at some point you will know the output of the function on all possible strings, although that will take a while. How many strings are there? Okay, 2 to the 15, that's a lot of strings. But yeah, what property does this function have? It has the property that, well, if it's taking, so think of the, I don't know if you like 0, 1 to the n is sometimes called the Boolean hypercube. Basically, think of all points in 0, 1 to the n. There are 2 to the n. Here, there are 2 to the 15 strings, right? And imagine connecting 2 strings if they have a Hamming distance of 1, meaning I can go from one string to the other with 1 bit flip, right? And now imagine that each of these strings are colored with one of 16 different colors. Okay, so imagine that that's the output of the function. It's assigning a color to each string, right? So if I'm standing somewhere in this space, right? So let's say I'm standing at the all zero string. How many neighbors, like how many strings are there which I can go in one hop, which I'm connected to by a single line? Sorry, how many? Yeah, that's just like each flip will give you a Hamming distance of 1, right? So from the all zero string, what are all the strings I can reach by flipping only one bit? That's all the powers of 2 basically, right? I can either flip the first bit or the second one or the third one and on up to 16 bits. So there's 16 possible strings that I can reach by flipping one bit. And now if I look at only those 16 strings, this function should have colored all those strings how? With the same color, different colors, mixed colors. Okay, so the function should have colored all of these 16 strings with 16 different colors, because if I'm at 0 the function's output is 0, right? Now from here you might ask me to go anywhere, right? I don't know. Right now the function's output is 0, and you might ask me to go anywhere from here, I don't know. So if you ask me to go to 12, there should be some string which has exactly 1, 1 in it, and the function gives it a value of 12. You might ask me to go to 10, so there must be some string which has 1, 1 in it, and its output is 10, right? So I don't care about which one, but all the numbers should be available so that no matter what you ask me to do, I can do it, right? So the way the function is we can check, if you ask me to go to 10, I will just go to 10 like that. Okay, so the function is on the 10th bit. I mean, this is, okay, I'm showing you a part of the function. I'm not showing you the entire function. But the function is such that, like on the ith bit, if you have a 1 and everywhere else you have 0, the output of the function is I. That's how you ensure that from 0 you can manage anything, right? So from 0, if you ask me to go to 0, so that is you don't change the value of the function, then I will just flip. I have to flip one bit. Let's say that's the setting. I have to flip one bit. Of course, if I was doing it like a magic trick, I would say, haha, we're very lucky. The function is already taking your favorite value. But if you forced me to flip one bit, then I can flip the 0th bit and the function would remain at 0. If you want 9, then I will flip the 9th bit and the function will become 9. If you want 5, I'll flip the 5th, actually technically the 6th bit, as in this is 0-based indexing. So I will flip the bit labeled 5 to get 5 and so on, okay? So do you see that 0 is a good place to be? Because from 0 I can easily go anywhere. But now I want to design a function which has this property at every string. At every string there are 16 adjacent strings, 16 strings that are reachable with one bit flip. So from this string, which are the 16 strings that are reachable? It's, this is one of them. All zeros is again one of them. That's one bit flip. This is another one. So there are all these 16 strings. And again, I want that all those 16 strings should take on 16 different values. So there are lots of constraints coming from lots of places, because every string is saying my 16 neighbors should be colored with, should take all 16 different values, right? So so the puzzle is, how do you design a function which achieves this effect, okay? Okay, so normally I'd say let's take 5 minutes to think about it, but maybe let's think about some of it together. I think that might help. Okay. All right, so first of all, visually I find it useful to think of the input as being written on a 4x4 grid. Okay, so this represents the string 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1. Okay, so just take your string and split it into blocks of 4 and then stack them one below the other. Okay, and the slightly lighter boxes are 0, and the darker boxes are ones. So think of it like that. And what does the function f do? It maps this thing to a number between 0 and 15. So you can think of a number between 0 and 15 also as being represented by 4 bits, right? Because 15 is, what's the binary representation of 15? It's 4 ones, right? It's 1 plus 2 plus 4 plus whatever the next one is, 8. Okay, yeah? So 15 is 4 ones. And think of f as writing out 4 bits. And the way this is going to work is, okay, so do you want to think about what the function, okay, so let me tell you what the function f is, okay? That those 4 lines of JavaScript code that you saw, let me tell you what it's doing. And then let's try to think about why this function has the property that we want it to have. Why does this function have the property that no matter where you are, you can always flip a bit to get whatever output you want? That's the property that we want it to have, right? Okay, so here's what the function is doing. For the first bit, it takes the bottom 2 rows and outputs the parity of the number of ones in those 2 rows. Okay, so how many 1 bits are there here? 3. So the parity is odd. So I'm going to output 1 as the first bit of my output. Okay. So this function may seem a little mysterious. I'm cutting short, these ideas will start occurring to you if you had 2 hours to think about it. We don't. So if it looks a bit like, where did it come from? That's okay. Just ignore that feeling for now. Okay. So on the bottom 2 rows, I get a 1. Then I go to the second row and the fourth row, okay? Go to the second row and the fourth row, and again I calculate the parity. Again you see 3 ones, so the parity is again odd, so I write a 1. For the third bit, I go to the last 2 columns, okay? And again I record the parity. What is the parity of the number of ones? It's 0, because there are 2 ones, so that's 0. And then again I take the second column and the fourth column, and the parity is again 0, right? So that's my output. What is this number in binary? 1100? 12, yeah, 8 plus 4, right? So the function on this bit string outputs 12, okay? And let's say you say your favorite number is 7, so I want to go from 12 to 7. Okay, I want to change 1 bit so that my output changes from 12 to 7. So let's look at, the current f is 1100. What I want the output to be is 0111, right? Because 7 in binary is what? 0111, right? So you see 1 smiley face, that's where I have a match, right? My current function is doing good on the second bit. The second most significant bit, it has the correct value. On all the other ones, I want to flip it, okay? So now can you tell me which bit I should flip to go from 12 to 7? So remember how we calculated, so the first bit I want to flip. So let me write down this box. Okay, how did we calculate the first? The first bit we calculated by saying, on the last 2 rows, calculate the parity of the ones, right? Now, I know that I have to flip something from the bottom 2 rows to fix that first bit of output. I have to flip something from here. The second bit is it's good for me. I don't want to touch it. Okay, so from the second row and the fourth row, I should not flip anything. Does that make sense? I should not touch those 2 rows. So in which row should the flip happen? Second. Does that make sense? Yeah, third from the top, second from the bottom. Both of you are right. Okay, so the flip should happen in this row. We have narrowed it down. flip should happen in that row, okay? If I was happy with the first output, unhappy with the second output, then the flip would have happened in this row, right? If I was unhappy with both outputs, then the flip should have happened in the last row, because the last row is the only one that touches both outputs. If I was happy with both the outputs, then the flip should have happened in the top row. Okay, because I'm like, all of these are good for me, don't touch any of it, so go to the top row, right? If I go to the top row and flip something, my first 2 bits will stay the same. Is that making sense? Yes? Sort of? Yeah? Okay. So we have narrowed down which row the flip should happen in. There are 4 possibilities. Either you're happy with both the first bits, or you're happy with the first, unhappy with the second, or you're unhappy with the first, happy with the second, or you're happy with both. Okay? Right? So depending on which of these scenarios shows up, a different row will say somebody should be flipped in this. Okay? And those were the cases we just discussed. I'm just repeating myself to make sure we are on the same page. Okay? Now it's the same story for the columns, right? So for the columns, what's going on? I'm unhappy with both the columns. So in which column should the flip happen? So the third bit was the output of these 2 columns. This is the third bit. And the fourth bit is the output of the parity of these 2 columns. Okay? So now I want to flip both. If I want to flip both, in which column should I flip? The last one, right? Because if I touch the last one, then I flip both, right? If some dibba in the last column is flipped, then the parity changes for both of the bits, right? And notice that the parity changes whether you make a 0 to a 1 or a 1 to a 0. The parity of the number of ones changes in both cases, right? If it was odd before and you made a 0 to a 1, then you got an extra 1. And if it was odd and you change a 1 to a 0, you lose a 1. So in both cases, you go from odd to even, okay? And the other way around. Okay, so we know that the flip should happen here and here, so this is the bit that should be flipped. All right. So that's the calculation. So that's the function and that's the calculation. Okay. This is how you know which bit should be flipped. When I was doing it with you guys, notice, okay. Okay, can you think of a shortcut for remembering that that's the bit that should be flipped? If you think about the position of that bit, what's the position of that bit? It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Okay, so I really want to explain this a little more, but I think it's a really nice exercise also to think about it. So notice that 11 turns out to be the XOR of 7 and 12. Okay, it's kind of intuitive. What does the XOR tell us here? Whenever something is good, on some location you're good, the XOR says 0. And if on some location you have a disagreement, the XOR becomes 1. Right? So here the XOR is going to be 1, 0, 1, 1. Right? Does that give us 11? 8 plus 2 plus 1 is 11. Right? And why does it give you 11? If you go back and take a look at it, think of, if you write down the locations of all these dibbas that we used for the first bit, what are these locations? These locations are the last, like these are numbers from 8 to 15. What is special about numbers from 8 to 15 in their binary representation? Do they have something in common? The most significant bit is 1 for all of them. So all of these squares share the fact that the first bit is a 1. Okay? So in some sense, we are asking ourselves, is the location where the flip should happen, is its first bit 1 or is it 0? right? This guy is telling us that the first bit should be a 1 because we have a disagreement, right? When we ask, what is the location of the second, like what is the second bit of the location where my flip should happen? That comes from answering this question, okay? So these fellows are all numbers where the second bit is 1. That's why I chose the second row and the fourth row. These are all the positions. If you look at the numbers, they're going to be 4, 5, 6, 7, and then whatever, 15, 14, 13, 12, okay? All of these numbers, if you write down the binary representation, they have 1 in the second position, okay? So if you say, yay, this is good, that means that wherever the flip happens, it should have a 0 in the second position. And that's why when you XOR 7 and 12, you get a 0 in the second position, right? So this is a lot like, again, binary search. Bit by bit, you're revealing the location where the flip should happen. Yeah, does that make sense? Yeah, it's like quite a bit of detail, but if you think about it, it'll all make sense. And then the columns are the same. If you think about what these columns represent, these are all the numbers where the third bit is 1. And these are all the numbers where these are all the odd numbers, basically, right? 0, 1, so that's 1 and 3, whatever, 5 and 7, 9 and 11, and 13 and 15, okay? So all the odd numbers, as you know, have a 1 in the last bit, right? So either the flip happens at a location that has a 1 in the last bit, again, that's revealed by the XOR. If you're unhappy with this position, the XOR will tell you that, it should be a 1. Otherwise, the XOR will tell you that it should be a 0, okay? So basically, the shortcut is your function is, if you want to go and play this when the website is loading. Sorry, don't know why. Okay, seems to be fine now, fingers crossed. So you basically see a random string, whatever this is, and some output 11, and you tell me you want a 7 or something, then what should I do? I should do 7 XOR 11, and whatever that location is, I should go and flip that bit. So that's how you do this performatively. I have a XOR calculator on my phone because I don't trust my mental XORing abilities. But if you're good at writing things in binary, taking XOR and then converting it back to decimal, good for you, you'll be able to perform this trick pretty efficiently. So I can do a little bit of mental XORing, but it's like, I get it right like 50% of the time. So there's a nice, like, there are lots of websites that can, like, you can write a little script. I've written a little script that does the XORing for me, so. Okay, cool. So in the last 15 minutes, I want to show you one last card trick, and then we'll be done. Okay. All right, so I have a deck of cards here. It's not like, if you feel it, you'll see that it's not a full deck. I need a row with, okay, can some 5 people come to the front bench? It's easier if, like, you don't have to sit on one bench. You can sit like 3 of you in the center and 1 each there. Yeah. I think we need 1 more person in the center. Sure. Okay, again, depending on if we have time and if you're interested, we can do this again. Okay, so I'm going to trust somebody with this deck, and you can give it a few cuts. Okay, so you can take, again, you know what a cut is, so take any number of cards you want and put it at the bottom. Okay, so lift some part of the deck and put it at the bottom. So we're going to do that a few times. And then I'm going to ask you to pull up the top 5 cards. I don't see what they are. And I will try to predict them based on some information that you give me. So I'll ask you to cut the deck since you've had a lot of practice with cutting. So, that's a totally random shuffle. Sorry. Okay, all right. Okay, so did you every time did you just give it a cut, or did you 3 cuts? Okay. Okay, that was very fast. Can you do it again? Slowly. Okay. Okay, so, that's a good point. I'm going to have to do a quick, okay, so, okay, let me just take a minute to talk about the difference between, So if you pull out some cards from the middle and put it on the top, that's not entirely a cut. So what you do with a cut is you take a fixed number of cards from the top and put it at the bottom, okay? What property do you think a cut preserves that like a random shuffle like that will not preserve? Relative order of the cards, okay? All right, so you can already guess like the first part of how this is going to go is that okay, I should have had a backup deck with the correct order. So if you give me okay, let's take a 2-minute break where I figure out. Okay, so the cut shuffles preserve a certain order. What I'm going to do is I'm going to give you the top 5 cards, okay? I don't look at the cards, I genuinely don't look at them. And I ask people who have red cards to stand up, okay? All right? And based on who has the red cards, I'm going to try and predict at least the first card and hopefully maybe even all of them, okay? Okay, he's coming from a room that didn't have AC, so. Okay, so I want you guys to take, are the steps clear in terms of what we are planning to do? Okay, but okay, so as you can guess, the first part of the trick, as you've figured out, is based on the fact that this deck is in a certain order. The first question I want you to think about is, how many cards do you think I have in my hand for this trick to work? It's not a full deck. I can already tell you that if you hold it, you'll see that it's fewer cards. There's one particular number of cards that will make this work. So take 2 minutes to think about that while I see if I can get back my ordering. Sorry? 43 is a good guess. It's still a little bit less. It's based on the fact that there are 5 people. I cannot do it with fewer than, okay, here's a hint. If there were fewer than 5 of you, I cannot do this trick. I need information from at least 5 of you. I can have more of you, but I need this 5-length signal. And what sort of a signal is it? How many possible different pieces of information can I extract from all possible responses that I can get, right? So on one day, maybe only the leftmost person stands up. When I do this trick again, maybe the middle 3 people stand up. So how many such combinations are there? And based on that, what's the size of the deck? That's a lot of hints. Okay, I'm going to hope that I restored the correct order. You did not shuffle it too much, so that's okay. If you're a real magician, you can actually do what happened. You can do like a number of really quick cut shuffles and make it look like a serious shuffle is happening. But between us, no secrets. What I'm doing is very carefully just I'm taking an arbitrary number of cards, just putting them at the bottom, okay? And this, as you know by now, this is just for show, because what this is doing is I put these cards in a special order in front of you. And what this is doing is it's maintaining the relative order of the cards, okay? So this you know already. Okay, so in the interest of time and in the interest of maintaining the order, I will just move on to the next part. So take the top card. Yeah, just the top. All right, so those of you who have red cards, please stand up. Oh my God. Okay, all right, I probably did mess up that order. Okay, all right, cool. Okay, that's a very special sequence. Okay, you guys can all sit down, that's easy to remember. So that's, let me think of the reds, sit down, that's fine. So let me think of the blacks as being zeros and the reds as being ones, okay? So because we all like CS people, we like our zeros and ones. So the string that I just saw was an all one string. How many such strings are there that I could have seen? Like anything could have happened, right? So any subset of them could have had black, and that could be spread out in any order. So basically I'm asking you how many bit strings are there of length 5? 2 to the 5, right? So what's the size of my deck? Yeah, if it's more than 32, this trick will not work, right? Because I have to somehow guess at least his card based on this signal, right? Now, if there are 33 possible, if my deck has 33 possible cards, I have to figure out one of 33 possible answers using one of 32 possible signals, right? So some signal will be ambiguous, right? No matter what the mapping I have in my mind. So I can only do this with a deck of 32 cards, okay? If I asked 6 people to come on, then I could possibly do it with the standard deck or even a bigger deck of cards, right? At least in terms of, I'm not telling you that just because it's doable that you can do it, but at least we know that if you have too much information relative to the signal, then you definitely cannot do it, right? So is it clear that if this deck had more than 32 cards, this trick would not have been possible, right? Because only one of 32 different things can happen, and each of those things should lead me to one card that I'm trying to guess. I'm trying to guess your card, okay? So does that make sense, kind of intuitively at least? Yeah? Okay. So I'm going to guess, let's see. So the question is like, what card do you have? And I think there was like a lot of 7 energy in the room. So do you have a 7? And do you have a heart? I mean, you have a heart, but your card is also a heart. Okay, all right, fine. So it's a 7 of hearts, okay? And now I'm going to try and see if I can guess. Okay, so the next part of it is just going to be, this is usually the most dramatic part of it, but now since you guys know that the order was rigged, this is just a matter of me knowing the sequence and confirming it for you. So you have a 7 of hearts, you have a 6 of hearts, you have a 4 of hearts. Yes? Okay. And you have an 8 of hearts and you have an ace of diamonds. Yeah? Okay. All right. So, okay, so that's the entire trick. The main thing is guessing the first card. Okay. After that, if you can ratta the sequence, then you can tell everything else. Right? So it's a sequence of 32 cards, and this is one sequence that's like my favorite sequence now. So this sequence I know quite well. And if you spend some time with it, like, you can basically memorize it. So once you know the first card anywhere in the sequence, because we only did cut shuffles, right? Once you know the first one, you know the next how many of them, right? So even if there are like 10 of you sitting here, I'll probably be able to do all 10. Does that make sense? Okay, so now what's the main question? The main question, what is the sequence, right? What's this magical sequence that makes this happen, right? So these sequences are, okay, I don't know how much time I have. Okay, only 2 minutes, so okay. All right, so, okay, so first of all, we use this kind of magic encoding. It's not a big deal. The first 2 bits, so in fact, the first bit tells me the color. That you already know, that's public information. If you stand up, I know you have a red card. If you sit down, I know you have a black card. So that's some amount of information already. Now, the second bit, depending on whether it's 0 or 1, tells me the suit, okay? So if it's 1 followed by a 1, it's a heart. If it's a 1 followed by a 0, it's a diamond. If it's a 0 followed by a 0, it's a club. If it's a 0 followed by a 1, it's a spade. There's nothing sacrosanct about this. It's just a convention that we fix for convenience, and then we try to design the sequence around this convention. If you want some other encoding, you can pick some other encoding, that's fine. Any encoding of 32 cards as like 5-bit strings will work. But if you want to perform, then you want an encoding that's easy to remember, okay? So this encoding is very easy to remember. The first 2 bits give you, the first bit gives you the color, the first 2 bits together give you the suit. So that's what we just discussed. And now the remaining 3 bits give you the number. Okay, so the remaining 3 bits range between 0 and 7, right? With 3 bits, you can express 8 possible numbers. So if you see a 0, you just treat it as an 8 because there are no zeros in a standard deck. So treat it as an 8. The other numbers are like, what did we see? We saw 111. 111 is a 7. So ABC is just the value of the card. Okay, so that's the encoding. So now if you know the sequence and you know this encoding, you have all the information you need to perform this trick. Okay. The only thing missing is what's the math that's driving it. So let me just very quickly tell you that what you want is a bit sequence which is such that no matter where you are, right? So the final cut could have happened anywhere. Just imagine that I have the standard deck and I cut it somewhere. Okay, so if I see this pattern, black, red, red, black, red, this pattern should not occur anywhere else, right? Because this pattern is giving me a specific card. What is it giving me? It's giving me spades, ace of spades, right? It's giving me ace of spades. So ace of spades occurs at this position of the deck. It should not occur. If it occurs somewhere else, I'm getting a mixed signal. I'm not like, that means some signal is missing and some signal is coming twice. It will not make sense. So I want to design a bit sequence that has this property. Okay, and these, I hope it's clear why we want this property. This is the signal that we got today, all ones, okay? And all ones doesn't appear anywhere else, so I know what's going on. There's a wraparound when you reach the end. So basically, this is a 32-bit sequence. At every starting point with a wraparound, if required, write down the next 5 bits. So you get a list of 32 5-bit strings. And if all those 5-bit strings are distinct, that means I have all my 32 cards showing up, right? Yeah? Okay, conceptually, this is like a little, like, yeah, it's quite a bit actually, so it took me quite some time to get used to what was happening. So if it's basically, just in case it's not making sense, don't worry about it. You have plenty of time to go back and think about it. But these sequences are called De Bruijn sequences and combinatorics. They have lots of applications beyond the design of card tricks, but the card trick is a very cute application. You can think about how do you come up with De Bruijn sequences? Do they even exist? It's not obvious that one exists, but for every power of 2, you can actually come up with a De Bruijn sequence. You can come up with an algorithm. You can come up with either a greedy algorithm or one that uses walks and graphs. That was part of what I wanted to talk about, but we are way out of time, so I won't bore you with all that. I will encourage you to go back and think about why does the De Bruijn sequence actually give you exactly what you want? And if you want to perform this trick, this is the sequence, okay? So for each of these bits, you can write down the card, right? Now you know. So that's clubs. That's 8 of clubs. That's the first card. The next card is going to be, okay, I should have done it the other way. So the first card is 8 of clubs. The next card is ace of clubs. Then I have 2 of clubs. Then I have, what do I have? 4 of clubs, right? And then I've switched from clubs to spades, and now it's ace of spades, and so on and so forth. So this is your 32 card sequence. You can basically, if you remember this bit sequence, you basically have the card sequence. If you find it easier, you can write down the cards and remember the card sequence. So at least I think you have all the information to go back and perform the trick. The math of it, I think, if you've already digested it, that's amazing. If you haven't, don't worry about it. Just, I think, meditating about it for a few minutes this will all eventually make sense. Okay, all right, so sorry about going a few minutes over time. I think we can skip the Q&A and make it informal. I'm happy to stay back for anybody who wants to discuss more. Also, you can find me on whatever social, like LinkedIn or wherever else, or you can send me an email. And if you mention Paradox, I'll make sure to prioritize and get back to you. But once again, I appreciate all of you being here. Thank you so much, and thank you for being such a sport with all the tricks. Okay, all right, so we'll stop here. Thank you.